Alright, so in this video I'm going to go through mathematical induction, and I'm actually going to take as example a sum sequence. Alright, there exists different formula which you can prove using the mathematical induction, but for this session we're going to use a sum. Okay, sum of a sequence, and then in the other videos we're going to explore different sorts of proofs. So let me write down the proof we have to do. So in this proof we are actually adding different numbers to the power of 3, so we're cubing different numbers, and then as outcome we need to get n times n plus 1 over 2 to the square. Okay, and this expression is valid for n greater or equal to 1. Now, there are 3 key stages when it comes to mathematical induction, with the first one being the testing stage, whereby you input a value and then you check whether the formula works. So if we take n equal to 1, okay, that means the first term, so that's 1 cubed, is equal to, you're replacing the formula here, so it's 1 multiplied by 1 plus 1 divided by 2 to the square. So that gives you 2 over 2 to the square, which is 1 square, which is 1. So you do get 1 is equal to 1. Okay, 1 cubed is 1. So the formula works when we replace it by 1. Now the second stage is we assume that it's true for n equal to k. Okay, we assume the formula is true for n equal to k. So if n is k, what happens is that we have that sequence, but then the n is replaced by k, so you're actually stopping at k cubed. So you replace n by k on the left hand side, and then you replace n by k on the right hand side. So you end up getting this expression, and if I use indices, this can be simplified to k squared, k plus 1 square over 2 square, which is, so we basically just shared the power, which we can do as per the rules of indices. So it's k squared, k plus 1 square divided by 4. So this is stage 2, step 2, whereby we assume that the statement is true for n equal to k. Then the third stage is that we need to prove it's true for n equal to k plus 1. And we actually need to prove that is true using the assumption. So using the assumption. So how do we work it out? What would happen if n is k plus 1? So I'll rewrite the expression. I'll replace n by k plus 1, so you get k plus 1 to the power of 3. This is the same as k plus 1. K plus 1 plus 1, so that's k plus 2, divided by 2 to the square. And once again, if I use indices, it's k plus 1 square, k plus 2 to the square divided by 2 square, so that's k plus 1 square, k plus 2 to the square divided by 4. So this is the expression I need to get for n equal to k plus 1, if the formula holds true. Now we need to prove that we can actually get this expression using the assumption. So just like with most, not most, but for all cases whereby we have a sum involved, we always use the same strategy. So the strategy is that if you're summing, if you're adding from 1 up to the k plus 1 term, and you're adding the general term un, this is the same as the sum from the first term up to the kth term of the sequence of the nth term plus the k plus 1th term. Okay, for instance, if you're doing sum of first 10 terms, it's the sum of the first 9 terms plus the 10th term. So that's the logic we're using here. All right. So if we use that logic, if we need to do the sum from the first term up to the k plus 1 term, which is basically the expression here, we need to do the sum from the first term up to the kth term, which is stage 2, which is step 2. So that's k squared, k plus 1 square over 4 plus the k plus 1th term. Now, in this expression, the nth term is n cubed. That's why the first term is 1 cubed, the second term is 2 cubed, the third term is 3 cubed. So the k plus 1th term will be k plus 1 to the power of 3. So this is what we get. And here I'm going to use LCM. If I use LCM, I get k squared, k plus 1 squared, plus 4 times k plus 1 cubed. Then you can see that you have k plus 1 squared common, so I can factorize it out. And if I do that, I get k squared plus 4 times k plus 1, that's left inside, over 4. And if you expand that, k squared plus 4k plus 4, that's actually k plus 2 to the square. Okay, so you end up getting k plus 1 to the square times k plus 2 to the square divided by 4, which is the expression we had to get if we replaced n by k plus 1. So we got this result using the assumption, because we used the logic that sum from the first term up to the k plus 1th term is the sum from the first term up to the kth term plus the k plus 1th term. And we had to use the assumption because this expression here, sum from the first term up to the kth term, that's stage 2. So we use the assumption to actually get an answer, which is the real answer, because if we replace by k plus 1, we get the same answer. So we've actually done the proof by induction. So usually you finish the question saying that since it's true for n equal to k plus 1, it's also true for n equal to k, and that therefore it means that the formula is true for all values of k. So that's how you would end the question. And I hope that this was helpful to introduce you to the mathematical induction. I didn't want to use a very simple example to explain the concept to you. And then the question you see on the board right now is actually an exam question. So it's a good one to use as an example and to go over again, revise, and actually practice it.